letting me be part of. Thank you for allowing me to be part of your symposium here today. And I've done a number of things at U of M, which I'll talk about briefly. And this is actually something I did some time ago, but when I was invited to present and I was talking about some of the things that I've done, I think it was thought that this is a bit different than probably most of the other presenters would be talking about. And so I was asked, even though this is kind of some old stuff, um, talking about this project that I worked on back around the turn of the century before many people on this call were even born, but that's all right. Some of the work that we did was, as I said, Mercury in the Everglades, and I want to talk a little bit about how ecosystems play a role in the cycling of pollutants. And I think that even though the data I'm going to show is a little old, and even though we're talking about a completely different ecosystem well away from our state of Michigan, I think the important thing is that I hope that we'll see when I'm done here is that wetland ecosystems, they're not only beautiful, but they're very active players in our global ecosystems. And I hope it can show a little bit about why their care is so necessary because of that a very important role that they play. So I'm just going to go ahead and get started. I'm going to tell you, you probably should know a little bit about me. So this is something I often show in my classes, so why not? Long before Instagram, that's me on the left-hand side with my sister. I don't know, gee, that might have been like 1970s or so, but the fact is that growing up in the state of Michigan, I loved when we got hit with snowstorms. I loved when we got school canceled. And so what I used to do is sit and watch the TV, listen to the meteorologist, and hope that they would tell us that school was canceled. And over time, I not only wondered if it was going to happen, but the scientist kicked in me, I guess, and I started to wonder why that was happening as well. At the same time, I also have this great love of radio. So this is before the internet, but I had this tiny radio that I could listen to baseball games all across the country. And so I kind of took those two things and I decided that what I wanted to do with my career, excuse me, was to be a broadcast meteorologist. So I went to the University of Michigan starting in way back in 1980, learned how to read all the weather maps and things like that, and eventually did fulfill my dream, if you will, at the time of being a broadcaster and working actually on the TV station that I grew up watching, and that's Channel 12 in Flint. Eventually, though, I wanted to learn more, and I didn't feel that I could do that in the current job I was at. Excuse me. So I went back to school and I got a graduate degree and eventually got my PhD and started teaching at Michigan and also doing research. And part of the research that I started doing was related to mercury. And that figure in the middle is showing the total amount of mercury that is, we call it wet deposition, but it's from rainfall. And you can see that there are certain parts in the country that are kind of red. It's almost like a heat map, if you will. And part of that is across the southern part of the United States, down in the Gulf Coast area. And Florida, in fact, had some very high concentrations of mercury in their water columns in the Everglades. And they actually thought that it was possibly attributed, or the death of wildlife, and including a Florida panther, was attributed to the high amounts of mercury in the wetlands of the Everglades. So they wanted to learn more about it. One of the things you get to do when you get to do research on this type of thing is you get to be creative as well. That picture on the left or on the right hand side kind of looks like a frisbee, kind of looks like a water bottle, and they are. And that what's on top kind of looks like your doormat, and it is. We were trying to figure out how can we measure particles and gases in the atmosphere that we're depositing toward the surface. So I mentioned rainfall, that's wet deposition. Dry deposition is when the particles and gases go down reach the surface. And so we had been trying to figure out how do we replicate what the ground actually looks like. And so I was mowing lawn one day and got to daydreaming, and I thought, I've got a doormat and it looks kind of like grass. So I wonder if we can use that as a kind of a surface that particles and gases will stick to. And it turns out it worked really well. So we put that on the frisbee. And if it rains, it would wash down in the bottle. And so we could measure that wet deposition, if you will. And then if it was just dry gases and particles, it would get caught up in that grass. And then we would be able to take that in the lab and measure that as well. And so we would kind of look at this and figure out how much was dry, how much was wet. And part of that measurement also was because we had just a what we call a wet only collector. That was that we would put right beside it as well. So got to be kind of creative and design some instruments for the measurements we wanted to take. In addition to, after I had worked in that area, I just wanted to say that some of the work that I'm doing now is actually related to climate adaptation planning. So Matt, in fact, I work with a group called GLISA, and Matt is now actually working with our group in a capacity as well. And what we do at GLISA is we kind of consider ourselves to be climate interpreters. You have numbers of communities that are trying to look at how our climate is changing and make decisions about how they can respond to those changes. But some of the data is kind of complex, some of it's really kind of voluminous. And so what we try to do is be kind of that buffer in between of trying to help the communities and other users actually be able to have access to that data. The picture that you see here is actually an indigenous or a couple of indigenous members, tribal members that are doing some wild rice harvesting. And much of the work that I currently do, in fact, is with working some of the tribal communities in the Great Lakes. So let's go back to mercury and say why do we care about mercury? Well, exposure to a form of mercury called methyl mercury it commonly occurs when people eat fish and shellfish that have high levels of methyl mercury in the tissues of the fish. And we'll kind of talk about why that's the case in a second. Methyl mercury is a neurotoxin. In other words, that means that if you absorb or if you consume enough methyl mercury, it can actually cause problems with your nervous system. And this is particularly the case during the development of a child when a woman is pregnant. And it easily passes through the body and into the brain and can affect things like cognitive thinking, memory, attention, ability to speak, fine motor skills and things like that. Anything that has to do, you might imagine with the nervous system. So a newborn might take longer to learn things if they have been exposed to high levels of methyl mercury, and if other adults are exposed to high levels of methyl mercury, they could start to see deterioration in some of those conditions as well. Mercury itself naturally occurs in the Earth's crust, but when we start to look at human activities such as mining, fossil fuel combustion, when we're trying to create power or other things, it ends up converting mercury into forms that are easily transportable around the entire globe. So we often refer to mercury as a global problem, even though you can have local hotspots. It is something that people all around the world are concerned about. So I kind of made some cartoons. I hope you don't mind, but I wanted to kind of describe the where this mercury comes from. So I said it's naturally in the crust. So we can have mercury being emitted from the soils. It can be emitted from volcanoes, and there can even be some in the oceans and lakes and streams that get emitted as well. Though when they come from the oceans and streams, there's some question as to whether it's natural or whether that's just a re-emission of what we call anthropogenic pollutants, which are due to human activities. And some of those human activities that lead to emissions are fossil fuel production. So mercury likes to adhere to sulfur. So in various coals, there's lots of mercury. Various other types of industries, cement kilns, waste incineration, are known to emit various forms of mercury. And I kind of have that picture off to the right. Artisanal mining, it's an old panhandler is what that picture is. But the reality is that it turns out that for many years, we thought that fossil fuel energy production was the major source of mercury. But then people started realizing that there are all kinds of small individual operations throughout the world where people go and they mine ores, and then they heat it up and they try to get rid of all the contaminants. So what you end up with is just gold. And that's happening all across the world. But the problem is that it turns out mercury really likes to adhere to gold. And so where you have gold, you often have mercury. And so as people are melting things down to try to get the mercury, or rather get the gold, you release mercury as well. And so that has ended up being a huge source. People throw things away, and unfortunately, including things like thermometers. And so sometimes things get into landfills, and so we might see emissions from landfills, and sometimes some leakage, if depending on how well, I guess, they are constructed. And then there is naturally mercury reaching the ground, and it can get washed into wastewater streams, sewage, and all of these can eventually find themselves into water bodies. And you know, I'm sure people have walked around the city and seen drains that say, you know, do not pour whatever goes directly to the river, or what, you know, that's the kind of thing that again can provide some mercury into water bodies. So what happens? Well, let me I just show you kind of all of the, I said it's a global pollutant, not only in the concentrations in the atmosphere, but where you can see the emissions. And you can kind of see in the center, and I'm going to annotate a little bit if I could. You can see kind of these areas here, sub-Sahara and parts of Central or South America. And this is where a lot of that artisanal mining is occurring, those really small individual mining operations. And that's where a lot of the mercury concentrations or mercury emissions are happening. And if we take, and let me clear that and get it out of that. If we take a look at where that's coming from, see, this is that artisanal mining. And like I said, when I started working in mercury, we just thought it was everything from coal combustion down. And in time, people started realizing that no, this small scale mining is a huge source of mercury, and it still is. And this is from 2018. And you can see that globally and on an annual basis, there's about 2.2 million kilograms of mercury that is emitted to the atmosphere. And that's about the same, a little bit more, but that's about the same of those natural emissions that I was talking as well. So both from a natural perspective and from human activity, we're putting a lot of mercury into the atmosphere. Now, most of that mercury is in the elemental form. Believe it or not, if you have fillings in your teeth, depending on the type of amalgam they used, there is often a little bit of mercury in there. And so you are an emitter of elemental mercury. You're not in industry, but you're emitting it. And most of it is this rather relatively benign form. About 95% of what's in the atmosphere is relatively benign. But it's these particle bound forms and reactive forms that actually, even though they're smaller in scope, they can play a big role because they easily take part in chemistry. So when we get it in the atmosphere, how does it, you know, what happens? Well, I mentioned that some of it dry deposits, and some of it either gets captured in clouds and then rains out, or some of the raindrops as they fall might actually intercept mercury particles or gases and carry them into a watershed. What happens then is there's a variety of little microorganisms that participate in all kinds of chemical reactions that help them out in water bodies, and that eventually leads to this formation of methyl mercury. But the concentrations are really, really small. You know, almost to the point where if you would hear someone talk about how much mercury is there, you'd say, like, why is that a problem? Well, here's why it's a problem. Even though there's a little bit there, you get all this methyl mercury, and all these little zooplankton and phytoplankton take some of it up, and then it gets eaten by these little small forage fish, and they get eaten by larger predator fish, and then eventually these large predator fish eat them. And so what was just very small, you know, amounts of this methyl mercury build up in a process that is called bioaccumulation. And eventually these are the fish that people are harvesting from taking from the rivers and the lakes or wherever, the oceans, and they're eating them. And so there's many parts of our country that wherever, you know, people will have boat launches, there'll be these signs that basically say the fish are probably contaminated, they have high levels of mercury and possibly other pollutants, and so, you know, do not eat them. So that's kind of how we get from all those emissions to these ecosystems, you know, allowing this through this bioaccumulation process of very low concentrations of mercury ending up being high enough in these fish that if significant amounts are eaten could cause some problems. So here again here's some updated data. This is from 2019. Actually, the 2020 hasn't shown up yet, but you can see again, here's this wet deposition. And so you can see that, again, even in Michigan, fair amounts of mercury are still being deposited. There's some hot spots elsewhere across the country. And even though these numbers are dropping a little bit in Florida, these are still some pretty high concentrations in the Gulf Coast states. And so something that they're concerned about. So we were part of a program with the state of Florida, and they've got kind of a unique situation. Here are the Florida Everglades, if I was to annotate again. The Everglades kind of come down here, and there's little parts of them here. I'm not doing a very good job of outlining, but you get the general idea, all right? And then that's right next to this large buildup area of urban and suburban homes and businesses and the like and industries. And it's right on the doorstep of the Everglades. So any kind of emissions you might be seeing from human activity is going to be able to get to the Everglades very, very quickly. So what we decided to do was we were going to try to understand the mass balance, if you will. Where's the mercury coming from? How much of it is getting into the Everglades, and then how much is leaving? And so here's my colleague Hong Zhang. He's now at Tennessee Tech University. But this looks like a small platform, but this is actually a very long platform that goes out into the Everglades. And we have all kinds of instruments here. We're measuring the particles and how much mercury is on the particles. We're measuring the dry deposition. There's more of those frisbees that we were looking at kind of close up before. Hong has kind of an interesting instrument here. This is actually nothing more than a cake pan. So it's a see-through cake pan with some holes drawn in it. And as the air gets drawn in, we look at the concentration of the air outside this cake pan. We look at the air concentration coming out of it, and we figure that whatever that difference is because of what's being emitted from the water. So that's what Hong is doing. Hong's looking at how much mercury is coming out of the water, that evasion that we talked about a little bit. The instrument over here, this is kind of the one that I was playing with, and I'll show you that one in a second. The vegetation in the Everglades, there's two primary kinds. One is called sawgrass, and you can see it right here. And the reason why it's called sawgrass is if you peel back some, you can see right here it kind of looks like sawtooth right here. And trust me, if you start peeling it away, you will cut yourself. So it's very sharp. And then these are cattails, and we see these around Michigan all the time. And in fact, I was just driving down Liberty Road this morning, and I saw a whole bunch of cattail in a wetland on the side of the road as well. So these two types of vegetation are predominant in the Everglades, and they play a very important role in mercury cycling. So here's kind of my setup. And what I'm trying to do is we've talked about the fact that I'm measuring that wet deposition and dry deposition to see how much goes into the Everglades. Then we are also trying to understand how much is coming out. So what I did is I kind of put up these two inlets, and there's a mercury analyzer right here. And so it would sample into this one, and then we'd sample at this height too. And the flux of mercury, either to the ground or away from the ground, excuse me, is related to what's the concentration difference. So you can imagine if if the concentrations are really high, say here, and very low here, we would see a positive number divided by that distance, and then the minus sign in front of this little constant means that the flux would be downward. And if highest concentrations were just above the vegetation, then we would know the flux was moving away. And so we would measure that, but because we're trying to understand what the role is of the vegetation, we measured other things as well. So this is from a couple of 2-day periods in 1999. So trust me, if you're going to study or do research in the Everglades, the winter is the time to go. I've been in July, and the Everglades are pretty nasty at that time of year. But the kind of the purplish here are the measurements of the mercury fluxes. And then these blue lines here are the solar radiation. So, right, and I've kind of started them later in the morning in these images, but you can see that the sun kind of peaks in the early afternoon, and then the amount of solar radiation we get drops down, and then eventually to zero. And that's what's on the right-hand axis here. And the same thing the next day. So what I want you to see is that where we were at, we noticed that once the sun, at night, there was almost no flux of mercury at all. This is like after 8, 9 o'clock, all the way to the early morning hours. But as soon as the sun came up, we would start to see mercury coming out of the Everglades. And then it would drop back down and nothing's going on. And then the sun comes up, then the mercury comes back up. And to kind of see if it was, related then to what's happening with the plants, this is CO2. Now we all know that when transpiration is going on, right, you got evapotranspiration going on, photosynthesis is happening with plants, they are taking in carbon dioxide. And so what you can see, and so it's coming toward the ground. And so that's a negative flux. So you can see that when we had, before the sun comes up, photosynthesis starts. And so the plants are pulling in CO2, both of these days, but that's also when mercury is being released as well. So it turns out that all the evidence suggests that plants are actively taking up some gases like CO2 and ozone or oxygen, and emitting also sometimes oxygen and mercury, and some other species as well, potentially. So it turns out that these plants that are in the Everglades are actively helping to release mercury from the Everglades during the daylight hours. Now, how would this occur? Well, here's the bottom part of cattail, right? So here's kind of a drawing in the middle, and we can see that here's a stalk of the cattail, and this is the root system. They call it the rhizome, and so you can see that as it spreads out, then we get another cattail that comes out of it. So it's kind of this linked system, transport system underneath the water in the sediments of the Everglades. And so what's happening is that the mercury, some of it that eventually settles into the sediments, can actually then be converted into a elemental mercury again and get released up through the plants. And that might seem kind of odd, but if you take a look at this cross section, well, this cross section is just of the leaf, and you can see that peeled away in this cartoon, you can see like all these little individual elements here. And if you take a look at this cross section here, again, they kind of show all these little individual elements. Well, on the right-hand side, here's an actual stalk of cattail that's cut in half. And you can actually see these are like little straws, right? That if the mercury is being taken up by the rhizome and by the root zone, can actually get transported up the plant and out of the stomata. And this little network here, these holes are called erychyma. That's the name for those. So I guess that one of the things this symposium itself is Green Michigan and about sustainability. And the work that I was sharing with you was about mercury in the Everglades. But I think one of the things that work really helped me to understand, and I guess I would hope was hoping to share with you, is that wetlands are very active. All right, there, we see this picture on the right-hand side. It's a little blurry, but it's, this is from northern Michigan, but it's very beautiful. You can imagine being out there and not hearing much traffic or whatever, these beautiful scenes. But it's not just sitting there. The plants aren't just sitting there. They're very active, and they're really helping to help keep these aquatic ecosystems vibrant. They're doing, as the vegetation is out there, it's spreading out, it slows down the flow of water through them. So if you've got a bunch of sediment, it doesn't travel well down the creek or the river that might be there. They can capture and process and store nutrients and contaminants. And in the Everglades, that is what they're doing with the mercury. So I wanted to show you this last one. This is I went out last night with my camera to Dexter and took a picture of the Mill Creek area, because I wanted to show you that communities are recognizing this and kind of leaning more toward the sustainability and in terms perhaps of our ecosystems. People are realizing that we need to maintain the natural aspect of some of these ecosystems. And this is an area where there used to be a dam, and now here's the bridge over Mill Creek, and you can see it looks like a truck moving across there. And you can imagine that, there might be mercury that's depositing from the atmosphere to the soil or to the roadway, or maybe oil or other things, right? But you kind of have this buffer zone between where this is and before it actually gets to Mill Creek, right? These different plants, and you can see some plants here alongside the walkway that can capture them. You can see also they've built up all these nice plants along the creek here on both sides. And here is from kind of this point here, I kind of a little bit above, I kind of took a picture this way. And you can kind of see right up, it's kind of out of the picture, but this is where downtown Dexter is. And so, if you get any runoff and things like that, it's going to get caught up in this vegetation before it actually gets to Mill Creek. So, again, kind of for me, the takeaway it wasn't so much, the cycling itself of mercury, but again, the fact that these wetland ecosystems and the ecosystems along our precious wetlands are active. They're not just beautiful, they're not just plants to look at as you walk by. They play a really important role in keeping waterways clean. And so, as you're, for me, that thing that I learned as part of that research has really made me want to make sure that, kind of talk to my kids about, the importance of these types of ecosystems and the things that we can do to try to keep these waterways clean and healthy. So that's all I have. So I'm going to stop sharing my screen now. And if anyone has any questions, I can answer those now.
Thank you so much for the insightful presentation.